So I think in about 5 seconds, we should be good to go.
Excellent.
Great. Well, let's get started then. So, yes, welcome to our final talk. Very excited to have you all here back with us to close out the weekend with the wonderful Professor Jim Al Khalili. I'm going to hand you over to your chair for this event, Joe, who's going to introduce Professor Al Khalili. So, yeah, let's get started. Great.
Thanks, Molly. So we're thrilled to be joined today for an amazing double header to close the conference and to announce the final results for the examination that we held yesterday. But just prior to that, we'd first like to offer a warm welcome to those who have joined from the public. Welcome to PLANCKS. Whilst our 3-day symposium of physics is now coming to an end, PLANCKS is an annual event and it's hosted by a different student committee each year. It's overall organised by IAPS, the International Association of Physics Students, and it's supported by the IOP, and as part of their programme of activities for the physics student community, for apprentices and trainees throughout the year. PLANCKS is just one of numerous events supported by the IOP and by IAPS that students like ourselves can organise, and each of which serves to bring people together to provide opportunities to take part in competitions, to discover physics, and to build some personal development. We would urge you to look at what else is taking place around the UK and Ireland by visiting the IOP website at iop.org and the IOP student community web pages. From the committee here at Kent, we'd like to say that hosting this competition has been both a great privilege and a joy, and that we would highly recommend volunteering to host this event yourselves. If you're interested in such a role, contact Julian. I'm sure he'll be very interested in hearing from you, and we look forward to seeing the next iteration of PLANCKS in the coming year. So now just a few quick pieces of housekeeping before we move on to Professor Al Khalili. If you've just joined, you'll have joined in listener only mode, and you can contribute your thoughts and questions in the chat feature at the bottom of Zoom. Please do send us your questions, as they'll be included in our group discussion and Q&A in about 45 minutes or so, which will follow this presentation. We'll do our best to answer questions and read out your thoughts and comments where appropriate, and we'll be monitoring the chat to answer some of your comments directly where appropriate. So, rounding off our exciting lineup from this weekend, we have Professor Jim Al Khalili to give us our final lecture, which is entitled The World According to Physics. Having received his PhD in nuclear reaction theory from the University of Surrey in 1989, Professor Al Khalili continued on to a postdoctoral position studying H-meson production at UCL before returning to his alma mater. Today, he holds a distinguished chair in physics as well as a university chair in public engagement in science at Surrey, wherein his current interests include open quantum systems and the application of quantum mechanics in biology. Additionally, Professor Al Khalili is a prominent author and broadcaster, having written 14 books on popular science and the history of science, which have been translated into 26 languages. His latest book, The World According to Physics, was shortlisted for the Royal Society Insight Investment Book Prize, and he is also a recipient of the Royal Society Michael Faraday Medal, the Wilkins Bernal Medal, the Institute of Physics Kelvin Medal, and the Stephen Hawking Medal for Science Communication, and he was knighted with an OBE in 2008. So please carry on, Professor.
Thank you very much, Joseph. I think you've got all my medals there, and I've got a swimming medal and all sorts. Hello, everyone. Good afternoon. Pleasure to be here, and very excited to be sort of rounding off this weekend of talks. I'm afraid I haven't been keeping up with the program, so I'm not quite sure which speakers have covered which topics. But okay, maybe hearing something again is always sort of quite useful because it sort of clarifies things in your mind. So I want to talk about, so let me just share screen. As Joseph mentioned in the introduction, I want to talk about the contents of my book that came out earlier this year. Honestly, trust me, this is not because I want to sell copies of the book. I mean, obviously, if you want to buy a copy, that's fine. But it's basically a culmination of where we are, our understanding of fundamental physics, the nature of the universe, the nature of space and time, and so on. Obviously, in this book, nor in this 40 to 45-minute talk, I'm going to be covering everything. So there'll be stuff, obviously, that I'm going to miss out. I'm going to aim it at, I mean, clearly the majority of the audience are members of PLANCKS, who are by and large final year university students studying physics, but I'm also aware that this has been opened up to sort of a slightly wider audience. So I'll try not to assume any prior knowledge that you have to have reached your final year of a physics degree in order to understand what I'm about to say. There are lots of books out there on popular science covering fundamental physics, and it seems more and more are published every year. Certainly ever since Stephen Hawking published A Brief History of Time, publishing of popular science has really sort of exploded. And there are a lot of excellent books covering everything we know about physics, from relativity to quantum mechanics to particle physics to cosmology to everything in between. What I do in this book, and I'm going to talk about in this lecture, is really try not to sort of cover everything. If you think about our knowledge of the physical universe like an island, beyond the shores of the island is the great ocean of the unknown. And so as our knowledge increases and we learn more, and we develop theories and we carry out experiments to test those theories, our understanding of the world around us grows and the island grows in size. This talk is really about an exploration of the shoreline, or part of the shoreline of the island, the very limits of what we understand. It's also my own personal perspective on some of these ideas. It's in a sense, it's my love affair with physics. My ode to physics is something I say at the very beginning of the book, the subject that I've spent my life dedicated to and thinking about. I mean, I fell in love with physics at the age of 13 or 14. I still, at that point, thought I might play for Leeds United. I still think I can play for Leeds United, actually. But physics became the subject that I knew I wanted to devote my career to. And so a colleague of mine suggested, if you put your thumb on this book, on the word physics, it becomes The World According to Jim Al Khalili, which sort of somehow stresses the polemical nature of it's not. What I don't do is try and sort of promote a particular theory and say string theory is correct, everything else is wrong, or anything like that. So where are we now? 2021, entering the third decade of the 21st century. Where is our understanding of the nature of reality? Where are we in our journey towards finding a theory of everything? In 1981, Stephen Hawking wrote an article asking, is the end in sight for theoretical physics? In fact, the very first paragraph, he says in this article, I want to discuss the possibility that the goal of theoretical physics might be achieved in the not too distant future, say by the end of the century, the 20th century. By this, I mean that we might have a complete, consistent, and unified theory of the physical interactions which would describe all possible observations. So what he's talking about here is a theory of everything. Now, this is not a theory of economics or social behavior or psychology, but of the physical universe. So unifying the forces of nature, understanding all phenomena out externally in the nature of our universe, whether or not we humans are there or not. Stephen Hawking said this in 1981 because he believed we were getting close to a theory of everything. And this is before we had the big revolution in string theory, superstring theory, which I'll say something about in a moment, which really began in the mid-80s. Stephen Hawking thought that, all we need to do is dot some I's and cross some T's and we'll know everything. His view, and the view of many other theoretical physicists at the end of the 20th century, and potentially even now, I guess, is similar to the one that physicists had at the end of the 19th century. By 1890, it was believed that most of physics was done and dusted, right? We had Newtonian mechanics, we had Newton's law of gravitation, we had Maxwell's theory of electromagnetism, nature of light, nature of electric and magnetic fields, we had thermodynamics and statistical mechanics. What more was there to know? And in that last decade, of the 19th century, we discovered the electron, the first elementary particle. We discovered X-rays and radioactivity. And suddenly there were these mysterious phenomena that we couldn't fit into any of our known theories or models of the universe. And then we hit 1900, and you get the quantum revolution, Max Planck, and then relativity with Einstein. And that leads to the birth of what we still call modern physics, even though it's over a century old now. So we were very far from knowing everything there is to know about the universe. The question is, are we making that same mistake again today? Well, we're not quite. The amount we understand about the universe, the amount we understand about the nature of all physical phenomena, and the technology that we've developed that built on that understanding is remarkable. We know so much, but that doesn't mean we know everything. There's still that ocean of the unknown ahead of us. If I think back to, well, let's just think back to over the last decade. Here are two examples of discoveries that are still being made. Now, you might say, well, these, in terms of importance, they're equivalent of the discovery of the electron or X-rays or radioactivity. But my argument is neither of these discoveries have revolutionized our understanding of the universe. So here's Peter Higgs, 2012, the Large Hadron Collider confirmed the existence of the Higgs boson. And it's the Higgs mechanism that Peter Higgs and others had predicted that would lead to the existence of such a particle, the Higgs boson. They predicted that in the 1960s, and in 2012 it was finally confirmed. Nobel Prizes all around, thank you very much. And just 4 years after that, in 2016, we confirmed the existence of gravitational waves. Now, the diagram here, the gravitational waves, the first gravitational waves event that was observed came from the collision coalescing of two black holes. They're not sitting there out at the orbit of the moon around the Earth. This is just not to scale. These two black holes were over 1 billion light years away. So the event happened over 1 billion years ago because it's taken these gravitational waves to reach Earth. They travel at the same speed as light, the maximum speed in our universe. So it's taken that long for us to feel the effects of this cataclysmic event of two black holes merging, sending out ripples through space itself. It's sort of, the analogy is like dropping a stone into a pond and watching the ripples sort of radiate outwards towards the edges of the pond. Well, this is a very large pond, and it's taken 1 billion years for those ripples to reach the shoreline where we are standing. And of course, if you think about the ripples from a stone dropped in the middle of a large pond, by the time they spread out and reach the edges, they carry very little energy per sort of unit of length of the arc of the circle, because it's being spread over larger and larger and larger circumference. Similarly, these gravitational waves were hugely powerful, actually shaking, stretching and squeezing space itself. By the time they reached Earth, they were very, very faint, which is why it's taken us so long to detect them. Nevertheless, it was an incredible achievement to be able to confirm this. Gravitational waves were predicted by Einstein's general theory of relativity exactly a century before they were seen and measured experimentally. So my point about these two examples is that although they are important, exciting, newsworthy, everyone's sort of talking about it, nevertheless, they were basically box-ticking exercises, if I want to be very blunt about it. The Higgs boson was predicted half a century before it was detected. Gravitational waves were predicted a whole century before they were detected. We expected to find them. Had we not found gravitational waves, or had we rather found experimental evidence that gravitational waves don't exist, or that the Higgs boson doesn't exist, that would have been much more exciting. Certainly, it would have been much more important for physicists, because it would have meant that our current theories and understanding are in fact not correct. And so they haven't really revolutionized or changed our understanding of the universe. Not in the same way that the discovery of the electron or X-rays or quantum theory of relativity have. In fact, if you think back, certainly over my career, the one big discovery that has shaken our understanding of our current theories of physical reality took place in 1998. And that was the discovery of discovery of dark energy. So here's my depiction of this dark energy, the mysterious force pervading the universe. Basically, to summarize, we've known the universe is expanding. We've known that since the late 1920s. Edwin Hubble saw distant galaxies receding away from us in all directions. The universe is getting bigger. What we thought was that that expansion was slowing down due to the accumulation of all the mass and energy in the universe that's putting the brakes on the expansion. It's like stretching a spring, and gravity's trying to slow the stretching down. And what we didn't know was, will the universe carry on expanding forever but slowing down, or will it stop expanding one day and recollapse in on itself in the big crunch? Okay, and all the textbooks until 1998, that's what they said. Those are the scenarios. Will it carry on expanding? Will it stop expanding one day, or will it recollapse in on itself? In 1998, it was discovered that in fact the universe's expansion is speeding up. By measuring the rate, the speed at which distant galaxies are receding from us, we could see by knowing their distance and how fast they're moving from looking at the Doppler, the redshift, that tells us how fast they're moving away from a source of light is moving away from you, told us that in the past, the universe was expanding more slowly than it is today. Therefore, the universe expansion is speeding up. And we don't understand what's causing this. We've given it the name dark energy, something that's winning the battle against gravity. But what we don't know is its nature. We have ideas, and we don't know if precisely how it fits into our current understanding of the universe. So that is unexpected. Now, there are other mysteries out there. We don't know what dark matter is made of. We don't yet have a theory of quantum gravity, the theory of everything that Stephen Hawking thought we were close to. And there are many other things we haven't understood. So, there's more that we need to explore. But why have physicists been obsessed with the theory of everything? Why do we think we should have a single unified theory, maybe an equation you can compactify and stick on a t-shirt that describes all physical phenomena and forces? Because maybe just there isn't. Why should there be? What's the motivation? Well, one motivation is because until now, this idea of unification, simplifying, finding connections between phenomena that we didn't think had anything to do with each other has been very successful. And we've seen it time and time again in the past. In this one slide, and I don't want to spend too long on this slide, I'm going to go quite quickly, but I'm going to fill it up. This is one of my favorite PowerPoint slides I've ever made, because it's unification of physics, starting from the very, very earliest advances to speculation about the future. I hope you're looking at this on a device where you can make out the font size, because I'm packing a lot in. Okay, here we go. Let's start with the first unifying concepts: the falling apple and the orbit of the planets. And no prizes for guessing who unified those concepts. This was Isaac Newton in the 17th century. He realized that the force that's pulling the apple down to the ground, apocryphally, as told by Isaac Newton himself, he was sitting under the apple tree on his mother's farm and contemplating the nature of the forces that are controlling objects. And he realized that the force that's pulling the apple down to the ground is the same force that keeps the Earth in orbit around the sun and the moon in orbit around the Earth. It's obvious to us now, yeah, that's the force of gravity. But back then, there was no reason to think that whatever was pulling the apple to the ground was the same as the force governing the motion and behavior of heavenly bodies. Okay, there was two completely different universes, completely different phenomena. So we got Newtonian gravity. That was the first unification. By the middle of the 19th century, we have electricity and magnetism being unified. First of all, Michael Faraday carrying out experiments with wires and magnets and so on. And then James Clerk Maxwell, the great Scottish physicist, who develops the mathematics. He develops the theory of electromagnetism, saying that actually electricity, electric currents, and electrostatics, and then magnetism are two aspects of the same fundamental force, the electromagnetic force. And Maxwell also links it to the nature of light. He says light is just an electromagnetic wave moving through space. So there's another bit of unification. Then also in the 19th century, there are people working on heat and energy and designing engines to do work. And at the same time, people like Ludwig Boltzmann are developing a new field called statistical mechanics. So those of you doing A-level physics or have done A-level physics, you remember in A-level physics, you learn about kinetic theory. You know, we talk about pressure and temperature and volume, and really that sort of bulk property of matter, you can zoom in and see it's all down to the movement of individual atoms and molecules. And that's what statistical mechanics linked to heat and energy leads to something called thermodynamics. So thermodynamics is another unifying idea. Then we move to the 20th century. We have space and time. Again, no prizes. Einstein in 1905 developed special relativity. Again, space and time. What's got space got to do with time? Well, Einstein says they're part of the same unifying concept, four-dimensional space-time. Depending on your state of motion, depending on your point of view, what some people see as a distance in space, others see as an interval in time. Special relativity, the mathematics involved in understanding it is actually quite straightforward, but the concepts, you know, the understanding what it actually means, well, that takes time. That takes, you know, a good chunk of your physics degree to get your head around that. Well, Einstein went further than that, of course. He then applies his special theory of relativity to Newtonian gravity and comes up with a new theory of gravity. He says that when Newton talks about gravity, he talks about two objects somehow joined by an invisible force, an invisible rubber band that pulls things together, that acts instantaneously across space. Einstein says, no, gravity isn't a force. Gravity is the shape of space-time. So objects that pull other objects towards them, how does the sun keep the Earth in orbit around it? What the sun is doing is curving space-time around it, and the Earth is just following that curved path. The Earth thinks it's traveling in a straight line, but because the contours of space-time are curved, that causes Earth motion to move in an orbit around the sun. So general relativity was revolutionary. General relativity, Einstein's theory, leads on to modern cosmology. It has taught us so much, from the Big Bang to black holes to the end of the universe itself. So nature on the very large is described by general relativity. I move down here to the very small. Atoms. By the turn of the 20th century, we were still arguing about whether atoms were actually real. Well, it was Ernest Rutherford and in his laboratory in Manchester, where he first understands what the inside of an atom looks like. Einstein had proved that atoms exist using maths. Rutherford does an experiment to look inside the atom and realize it's made of a nucleus with mostly empty space and electrons buzzing around the outside of the nucleus. That leads us to the notion that where we thought there were just two forces of nature, electromagnetism and gravity, neither of those could explain how the atomic nucleus holds together. And that leads eventually to the understanding that there are other forces inside the nucleus, a new type of glue that pulls matter together. Jump up here now to quantum theory, again, the beginning of the 20th century. That leads then by the 1920s to quantum mechanics, which is the most powerful, the most important theory probably in the whole of science. Quantum mechanics then becomes the means, the mathematics that we use to understand the world of the very small. So quantum mechanics is used to explain special relativity is joined with quantum mechanics, and we get something called quantum field theory. Quantum field theory is then used to explain electromagnetism, and we get quantum electrodynamics. I'm going to speed up now. The nuclear forces, the strong force and the weak force, we use quantum mechanics to describe their behavior. The strong force, we develop a quantum theory for the strong force. That becomes quantum chromodynamics. The weak force is unified with quantum electrodynamics. We get electroweak theory. Electroweak theory and quantum chromodynamics put together give us the standard model of particle physics. So I've sped up my unification story. We now have an umbrella picture of the world of the very small. We call it the standard model of particle physics. It describes three of the four forces of nature: electromagnetism, the strong and weak nuclear forces. In fact, is that fourth force really a force at all? It's gravity. Sometimes we talk about it as a force, sometimes we simply talk about it as a shape of space-time, but it doesn't fit with the other three forces. We don't yet have a quantum field theory version of gravity. Cosmology, general relativity, of course, leads to another standard model, the standard model of the very large. So we've got the standard model of particle physics. We also have the standard model of cosmology. So those letters there are lambda CDM. Lambda is a Greek letter. That stands for something called the cosmological constant, which appears in Einstein's equations of general relativity. CDM stands for cold dark matter. So between them, lambda CDM are really reminding us that our standard model of cosmology is missing information. It's missing these two things: dark energy, which I talked about earlier, that's forcing the universe to expand ever more quickly, and dark matter, which would probably better be called invisible matter or transparent matter, which we also know exists out there. In fact, it doesn't act against gravity, it provides its own additional gravity, and it's needed to hold galaxies together. It's fundamental for the structure of the universe. So we know dark matter is out there. Like dark energy, we don't fully understand it. We don't know what it's made of. But they would have to be understood to feed into this standard model of cosmology. Would that be the end of unification? Well, no. I haven't even given the step that Stephen Hawking was alluding to back in 1981. He wanted a theory of everything. That's a theory that will bring together the standard model of cosmology and the standard model of particle physics. We call it a theory of quantum gravity. Quantum coming from the very small, gravity coming from the very large. We're not there yet. Why? What's missing? I'm going to give you, say something about the leading candidates. My argument would be that if we think about, we have pillars of physics. We have quantum mechanics for the very small. We have general relativity for the very large. We have a theory of the middle ground, somewhere in between, and that's thermodynamics. So there's a strong argument to say that we will not get to a theory of quantum gravity unless we also incorporate thermodynamics. Now, before I move on, there are a few gaps on this slide, and so I just tried to fill them in. So what else don't we know? Well, certainly quantum information is a new area of physics, and we're hoping to develop quantum computers, which may help us address the issue or lead us to the correct theory of quantum gravity. there are other areas which may or may not play a role. Nonlinear dynamics, far from equilibrium, thermodynamics, complexity theory, and even one of my favorites, the black hole information paradox. Look it up, it's fun. Basically, it's bringing together thermodynamics and general relativity. The idea that information cannot ever be lost, it's conserved somehow. But if you throw a book into a black hole, not only does the book get squashed up down to the singularity, but the information that the book contained, the words, that information is lost from our universe forever. And that seems to not sit comfortably with us. Where does it go? So these are still outstanding problems that we're trying to understand. But there are lots of physicists who believe that we're getting close to a theory of everything. I depict it here by an arm wrestle between two superheroes, right? So you've got on one side, you have the string theory, who's trying to unify all the forces of nature. Then you have what's called loop quantum gravity, which is trying to quantize space-time itself. There are community physicists who work in one area. There's another community working in the other area. Depending on where you work, I'm not saying it's all about getting where your bread is buttered and where you get your funding, but there are good reasons for people who are specialists in either of these fields for believing that they are on the right tracks. But the point is, we don't yet know if either of these ideas is going to turn out to be the correct theory of quantum gravity that describes our universe. And one of the issues is that we don't yet have a means of testing either of these ideas. So for now, in a sense, if I wanted to be harsh about it, they are really very clever maths, very powerful and elegant mathematics. But powerful and elegant mathematics doesn't necessarily mean that it describes our physical reality. A scientific theory should be one that we can test. It should be one that we can falsify, that can make predictions that we can go away and design experiments or make observations to measure against. And we don't yet have that. So we don't yet know. Maybe it's a case of going back to basics. Maybe we're trying to understand the nature of space-time itself. What is space? What is time? Many thinkers over the years have really struggled to understand whether space is a real thing, whether it exists in and of itself, or whether it only exists because it's got stuff in it, right? I'll give you an example. Imagine you have a cube, an empty box that's completely empty inside. It's a vacuum inside. Now, I know in quantum language, we say, well, nothing's ever really a vacuum. You have particles popping in and out of existence all the time. Let's put that aside for now. A box filled with completely empty space. Does that space exist because the walls of the box exist? What if I were to take the walls of the box away? Does that space still exist? Or did it only have a reality because of the walls of the box? Now, people like Aristotle, philosophers like Descartes, believed that space isn't real. It's only real because of the nature of it. So it only exists here because there are confining walls of the box. Newton believed that space was a real thing. It didn't need matter for it to exist. You have space and then you put stuff in it. What if this box then was embedded in a larger empty space? And now oops, sorry about that. Sorry, my phone falling on the floor. What if I now remove the walls of the smaller box? Does its volume, its space inside now have a more real existence because it's part of a larger volume? So these are, sort of simple yet sort of quite fundamental questions. Where do we stand today? Well, today we would follow Einstein's picture of what space is. In 2016, so very soon after he published his work on general relativity, Einstein wrote this book, Relativity, the Special and General Theories, published first in German, then translated into other languages. And he kept adding appendices to it with new additions rather than changing things. You know, he basically figured out relativity theory and wasn't going to change his mind about it. But his own thinking was clarified over the years. And we reached the final Appendix 5, which appeared just 1 year before Einstein died. In it are some of the most profound definitions of reality ever conceived by the human mind. Einstein, for example, says, if we imagine the gravitational field to be removed, there does not remain any space-time, but absolutely nothing. So he's not talking about walls of a box. He's saying gravitational field is due to matter and energy. So he says, if you remove the gravitational field, basically if there's no matter or mass or energy, you remove the gravitational field, then there is no space-time either. So he's almost saying what Aristotle and Descartes were saying, that space-time doesn't exist unless there's stuff in it. Space-time does not claim existence on its own, but only as a structural quality of the gravitational field. In fact, what Einstein's saying is space-time is the gravitational field. There is no such thing as space-time if there isn't a gravitational field, if there isn't matter and energy. If you look at Einstein's equation of general relativity, it's an equation. I won't go into the details of it. It's an equation. It's got an equal sign. That's all you need to know. On one side of the equal sign describes matter, mass, and energy. On the other side is space and time. So if one side is 0, the other side is also 0. Neither can exist alone. So Einstein, you'd say he would side with Aristotle. Space-time doesn't exist without stuff in it. But he also sides with Newton in saying that space-time is a real thing. It's the fabric of reality itself. You can stretch and bend space-time because that's what matter and energy does. You can warp it. If it wasn't a real thing, you couldn't do things to it. Gravitational waves that we measured a few years ago are ripples in space-time. These are ripples that, you know, there must be a something that is being rippled, right? And yet it can only exist when there's matter and energy. Okay, so these are the sorts of profound ideas that we have to remember. I don't want to go through quantum mechanics, but I just want to say something about the nature of time. Again, a profound idea that you'd think we'd have figured out by now, that we've have for millennia tried to understand, and you know, you think with our modern theories of physics that we've got it all sussed. But let me remind you of those 3 pillars of physics: general relativity, quantum mechanics, and thermodynamics. They each give different definitions to the nature of time. General relativity will say time is part of the physical fabric of the universe. It's a dimension. It's the 4th dimension. It can be stretched and warped by gravity. Time is a dimension. Quantum mechanics, on the other hand, says no, time is just a number. It's a parameter. It's something you plug into your equations of quantum mechanics, like the famous Schrödinger equation. You know, give me a particular time to describe the quantum state of something, say an electron. Crank the handle, solve the equation, and you can work out what that quantum state is, what that electron is doing at some later time. You can even crank the handle backwards and work out where it was in the past. The equations of quantum mechanics move forwards and backwards in time, because time is just a number. You can make it bigger, you can make it smaller. So time is a dimension, time is a number. Thermodynamics, on the other hand, says no, it's not a dimension or a number, it's an arrow. It has a direction. It points from past to future, points in the direction of what we call increasing entropy, increasing disorder. Here we have our 3 fundamental ideas, pillars of physics, all giving us different definitions of what time is. If we can't have a unified definition of the nature of time, how do we expect to arrive at a theory of everything? part of my research now is looking at the connection between two of these three pillars, not general relativity and quantum mechanics as is traditional, but between quantum mechanics and thermodynamics, quantum thermodynamics. How does an arrow of time emerge from quantum mechanics? Okay, how do we go from something that can move forwards and backwards in time to something when you make a measurement that points from past to future? So, there are still these big foundational questions out there waiting for us to be answered. And we should not be so arrogant as to think that we're getting close to the final solution. And in a sense, that's good, right? It'd be boring for me if we knew all the answers. Certainly be not very exciting for any of you who hope to go on to have a career in research in physics if there's nothing exciting left to be discovered. Einstein himself, on this issue of time, or certainly on the issue of the importance of the different pillars, he says thermodynamics is the only physical theory of universal content which I am convinced will never be overthrown. Isn't that incredible? You'd think that Einstein would basically big up his own theory. He'd say general relativity is the only thing that will never be changed. Quantum mechanics, we knew quantum mechanics. He was, unhappy about quantum mechanics and believed it was incomplete in a sense. And you'd think that he'd say, well, quantum mechanics has to change, but general relativity is sacred. No, he says thermodynamics is the thing that's not going to change. He's not ruling out the fact that general relativity may have to be modified or advanced or replaced by something grander. That it's not wrong, but maybe it also is incomplete. One of the questions that comes up, I want to give an example of why we think there are still so many questions to be answered. And as a popular question comes up, what came before the Big Bang? Well, you see, if you just use general relativity, there's an answer which is straightforward. It may take a while to get your head around it if you haven't thought about it. But general relativity will say there is nothing before the Big Bang because there's no time before the Big Bang. It's the same as being told to walk to the South Pole. And when you get to the South Pole, keep going south. It's a meaningless statement, right? Because any step you take from the South Pole will take you back north again. So there is nothing further south than the South Pole, in the same way there's no time earlier than the moment that time itself began, when space-time was born in the Big Bang. However, there are current ideas suggesting that maybe our time began for our universe at the Big Bang, but that was just our Big Bang, that time actually is eternal. I want to end with just saying something about another idea in physics, which is still, it's controversial in the sense that it hasn't been confirmed experimentally yet. And it's called inflation theory. Now, inflation was devised to explain some problems in cosmology. The notion that after the Big Bang itself, that within the first fraction of a second, the universe, space-time had to expand. Space has to expand very, very quickly in order to iron out lots of creases, in order to solve certain problems in cosmology. So this rapid expansion was called inflation, and then expansion of space settled down to some more sedate expansion rate until it started speeding up again now. But it's not speeding up now anywhere near the rate it would have expanded in that first fraction of a second due to inflation. So a lot of textbooks were talking about, you had the Big Bang, the beginning of everything, then you had inflation, and then our universe we see it now was formed slowly with galaxies and stars and planets. And a newer idea, which many cosmologists now buy into, has it the other way around. It has inflation and then the Big Bang. Something called eternal inflation. There's a larger multiverse out there. Okay, my favorite slide. You can never guess why it's my favorite slide. There's a multiverse of bubble universes. Time goes on eternally. Outside of these bubble universe, there's inflation going on all the time and has been forever. But every now and again, you get a little seed, a little dot somewhere within this, what's called the inflaton field, where inflation stops and you get a little Big Bang creating that universe. We exist in one of these bubble universes. Like string theory, like some of these other ideas, this is a highly mathematical concept. It solves problems. It would be very convenient if it were true because it solves other problems. But again, it's like a religion, you know, because you sort of have to have faith that it works. But of course, it's more than religion because it has mathematical foundations. But in terms of proof, is it a scientific theory yet? Well, we haven't yet found a way of talking about it. And so, where are we now? Well, I would argue that, you know, there are physicists who say we should not be spending money on building larger machines than the Large Hadron Collider. We should not be diverting so much of our theoretical effort into string theory or into speculative areas of cosmology because we don't know how to test them. They're not even proper science. I would argue that they are proper science, it's theoretical physics. We just have to be more imaginative in finding ways of testing these ideas. And that's what makes research so exciting, that there's still so much we have to understand. We don't know how to do it, but then if we knew how to do it, it wouldn't be as exciting. There's this ocean of the unknown beyond our island of knowledge. We can roll up our trouser legs and wade out and sort of walk around in the shallows and say, oh, dark energy, dark matter, is string theory correct? Is eternal inflation correct? What happens to information when it falls into a black hole? How close are we to unifying quantum mechanics and relativity? All those unknowns. But we don't know what lies beyond. Will we ever reach the end of physics? Does that ocean of the unknown go on forever? My personal view is that there is an objective reality out there. The universe behaves the way it does. There's an ultimate truth about the nature of reality. We are trying to reach it. We just don't know how close we are to getting to that ultimate truth. We may get there in the next decade or two. We may get there in 100 years. We may never get there. We may need the help of artificial intelligence to help us solve some of these complex problems. But that's what makes research in physics in some of these big questions so fascinating. Thank you very much for your attention.
Thank you very much, Professor Al Khalili. That was a fascinating talk. And in a similar vein, we've got some fantastic questions in the chat here for you as well. So okay. We'll go chronologically. The first and quite interesting question came from Hassan Al-Hamzawi, which is, either we'll eventually come to acquire a universal theory, or we never will. And which fact would you find more discomforting?
Oh, I think I'd find it much more discomforting that we won't find a universal theory. I mean, a theoretical physicist, well, any scientist wants to find answers. We're curious about the world around us. Yeah, if we did find it, it will be sort of, I mean, after the initial euphoria of understanding everything, we then feel a bit flat. Oh, okay, so what do we do now? But it would be very disappointing, disquieting to think that we would never be able to find the answers.
And the next question came from Louis Forrester, which is, do you agree with Einstein's statement that thermodynamics will never be overthrown?
I don't know. I certainly think that in modern physics, very often, particularly when people are looking for a theory of quantum gravity, they've, to some extent, not taken thermodynamics seriously enough. The nature of the arrow of time, the direction of time, I think is, as explained or predicted by thermodynamics, I think is fundamental and will be fundamental to our understanding of reality, both on the small scale, quantum scale, and on the very large. I guess I can't imagine something like the second law of thermodynamics is going to be overthrown. But we do know down at the quantum level, we can sort of break the second law a little bit. We can, there's a new kind of thermodynamics down at the quantum level that we're still trying to understand. So I don't think it will never be overthrown. It may be expanded a little bit, but I'm not willing to put any money on one area of physics being done and dusted and untouchable. Everything should be up for grabs.
This next question came from Professor Paul Strange, which is time really just a number in quantum mechanics when time reversal symmetry is broken by the weak nuclear force?
Well, yes, time reversal symmetry is broken. I mean, I'm taking a very simplified view of how you put T into an equation, a quantum dynamics equation like Schrodinger's equation or the Dirac equation, and you can replace T by minus T in those equations, and you can run things forward and backwards. Yes, time reversal symmetry is broken, and I think to some extent that should hint to a direction in time. We have different people talk about different arrows of time. There's the thermodynamic arrow of time. There's the cosmological arrow of time. There will be arrows of time due to symmetry breaking. Depending on which area of physics you come from, you see certain things as a larger or smaller problem to be dealt with. And I think for me, that simply means that we haven't quite understood it. If we're still arguing about certain aspects of, say, the nature of time, then that suggests there is still more to be understood.
In that vein, how might a quantum thermodynamics resolve the kind of the Feynman conception that positrons and antiparticles are just particles that are traveling backwards in time?
I've never found that idea useful enough to take literally. Positrons being on a Feynman diagram, yes, that's an electron moving forward in time is equal to a positron moving backward in time, or vice versa. That's a useful way of solving problems in quantum mechanics, but I don't think of that as that it should be taken literally, that it really is a positron, really is an electron moving backwards in time, because that then butts up with ideas, for example, in relativity. But certainly there will be links between thermodynamics and quantum mechanics in trying to understand one of the big outstanding problems in quantum mechanics, namely what's called the measurement problem. How does a quantum system go from being time reversible to being something that what we call is non-unitary? So it moves from past to future, and that happens when you make a measurement. And we're trying to understand the process. Making a measurement doesn't mean someone with a PhD opening the box with the cat inside. It doesn't necessarily mean the quantum world's interacting with the classical world. It simply means a quantum system has to be influenced or affected by its surrounding environment. So we're trying to study something called decoherence, which is in the same way that a hot object in thermodynamics leaks its heat out into the environment. Similarly, a quantum system leaks its quantumness, its quantum coherence out into its surrounding environment. It becomes entangled with a larger environment, and that entanglement leads to this breaking of unitarity and irreversibility of time. So in that sense, is how we make measurements in quantum mechanics has links with thermodynamics and classical mechanics that is something we're still trying to understand well.
Another question which came from Professor Sylvia Ramos was to thank you for a fantastic talk, and then says, I feel you avoided using the I word, specifically information. Why would that be? E.g., isn't thermodynamics best described as a unification of energy and information?
Yes, it is. And this, I recently gave a talk about Maxwell's demon. This is the so-called demon that can lower entropy in a box. A famous example that Maxwell came up with in the 19th century, that you have a box just in thermodynamic equilibrium with molecules. Some molecules are moving fast, some molecules are moving slow. Then you stick a partition in the middle with an opening in it, and the daemon can open that partition at special times to allow fast-moving molecules to go one way and slow-moving molecules to the other way, and gradually separate out the box into cold and hot halves. In doing so, ordering them, lowering the entropy of the box, so breaking the second law of thermodynamics. And of course, the resolution of that, and certainly with the work of people like Leo Szilard in the 20th century, explained that, well, what's happening, the daemon may have lowered the entropy of the box, but has increased entropy in his brain because he had to gain information about where those molecules are. And that link, I absolutely agree. The link between information and energy is crucial. And I think I sort of nodded towards that in my unification slide, where I said information theory and quantum information, somehow vaguely with a dashed line pointing to our theory of everything without saying any more about it. So yes, certainly I think one of the big growing fields in research in physics is information, quantum information. And it's sort of indicative of how much we had yet to understand when we just throw, as I'm doing, concepts together. Oh, quantum information and thermodynamics and it's all got to come together in some way. We don't yet understand it, and this is still a very active area of research.
Okay, we've got a couple some more cosmological questions now. This one came from Ada Elliott, which was, a few years ago, a new theory of dark gravity was proposed. What does it fail to explain, and is it still viable based on the knowledge that we have today, in your opinion?
Well, I mean, I have to say, I'm not a cosmologist, right? So I'm a quantum physicist. So I'm not quite sure what that theory would have explained. No, I think rather than just waffling on something I don't know about, I have to admit I don't know what dark gravity is. Maybe the questioner can, or maybe we don't have time for.
We've got another 20 minutes or so, but yes, if the questioner posts a clarification in the chat, I will update you.
Okay.
Some more hypothetical questions then from Rob Tate. Do you believe that the publicity given to more non-scientific hypotheses, like the many worlds interpretation of QM or the simulation hypothesis, undermine or support the perception of physics and science amongst the wider public?
I think certainly the wider public are, because of the popularity of some of these ideas in physics, and because they're being disseminated through popular science books and online and so on, people are hearing more and more about some of these more speculative ideas. And yes, to some extent that is true, that, it doesn't help when people like me say, are they really proper science if you can't test them empirically? But they are actually proper science. And the many worlds theory of quantum mechanics, which is a way of explaining or giving a narrative to the mathematics of quantum mechanics, whether or not it's the correct way, my view is that it's absolutely vitally important that we do find the correct interpretation of quantum mechanics. Now, here, not every physicist would agree with me. But quantum mechanics, let's face it, it's the only theory in all of science that's got away scot-free with not requiring an interpretation that we're all agreed upon. The example I always use is Einstein's special theory of relativity. The maths for special relativity was pretty much done and dusted before Einstein. People like Fitzgerald and Lorentz and others had developed, Poincaré, they developed the mathematics, what's called the Lorentz transformation equations. Einstein gave the correct interpretation of those equations. He said light travels at the same speed for all observers. There is no ether, right? You get length contraction and time down. So he gave the story, the narrative, the interpretation of the mathematics. And it's Einstein who's credited with special relativity. Now, in quantum mechanics, we have all the mathematics, and we've got half a dozen or more different ways of explaining what the mathematics means. Now, either there are many worlds or there aren't. Either there's a Bohmian quantum field pervading the universe or there isn't. Either you've got information traveling back in time, transactional interpretation, or you don't. There are lots of ways of explaining quantum mechanics, but they can't all be right. And I think it's intellectual laziness on the part of physicists for the last century almost, that we haven't been concerned enough. Because quantum mechanics works, because mathematics has led to the technology that's allowing us to have this conversation online, we sort of, it doesn't matter. Leave that to the philosophers, to the philosophizing. You know, we want to, quantum mechanics works, we want to use it. I would argue, no, we are putting knowledge to use. That's the job of engineers. A physicist wants to understand the nature of reality. And to understand that, we need to know what is the correct interpretation of quantum mechanics. And in that sense, something like the many worlds interpretation, or any of the other interpretations of quantum mechanics, I think we need to get across to the wider public that this is not just philosophical navel gazing. This is really a way of trying to understand what's happening at the quantum level in the same way that Einstein had to understand the meaning of special relativity in space-time.
Great. We have time for just one more question, if that's okay with you. Joe, go ahead, pick.
Oh yes, which one to pick? I suppose leading on from that then, there are two questions which effectively overlap somewhat from Nilesh Shroff, and I'm afraid I can't pronounce that name either, which are, so in your opinion, do you believe that it is within the realm of physics to be able to find this answer? You know, it's the role of physicists to understand physical phenomena and be able to produce these theories. Do you think that we will actually be able to find this absolute truth to some extent, or well, that's a bit philosophical, but this absolute idea, this correct idea for quantum?
Yes, I think it's our job to try. I'm not saying that we will be able to or when we'll be able to, but in the long-ranging debate in physics and philosophy going back 100 years, sometimes people frame it in terms of an argument between Bohr and Einstein, or philosophers will frame it in terms of argument between what's called epistemology and ontology. You know, is the job of science or physics to know how the world really is? Is there a reality out there? Or is it simply telling us what we can know, but we can never actually say what it is? All it's giving us is, you know, state of our knowledge of the. I'm a scientific realist, philosophically. So I believe there is an objective reality out there, a truth, if you will, you know, about the way things are, the way they are, whether or not humans ever existed on Earth. You know, the universe behaves in a certain way. And this is the job of physicists. I would side here with Einstein and say it's the job of physicists to try and find that objective reality, you know, the nature of how things really are. It's a different question as to how successful it will be. You know, lots of very clever people have tried very hard to find the correct interpretation of quantum mechanics for 100 years. We haven't got there yet, but that doesn't mean it's not out there, and it doesn't mean we should stop trying.
Thank you very much.
Great. Thank you so much for joining us again. A great way to round off the weekend and the events for today. So we're going to go into a 10-minute break now before the closing ceremony starts at 5:15. So all participants, please make sure you're back for that. And any members of the public that joined us for these first events this morning, it was great to have you.
Hi, Nigel.
So we'll be back in 10 minutes. Thank you again, Professor Al Khalili, for joining us.
Yeah, thank you, Jim.
My pleasure. My pleasure. Thank you for the invitation.
Sorry, I missed the first couple of minutes. You're keeping well?
Yes, very well. Working hard from home.
I admire your tidy bookcases.
Do you know what? I normally do all my Zoom and work up in the study upstairs, but I thought today is something. Do you know what? I'm going to do what every other one does, and you know, whenever they're on Zoom, always have a bookcase behind you.
Yeah, mine aren't quite so tidy, you see.
Well, this is the library room rather than my study with all my files and things, so I can.
Well, thanks a lot for doing it, Jim.
My pleasure. Nice to see you, Nigel.
I hope we get a chance to get you down to Canterbury. I know we've tried a couple of times, so I'm sure. But thanks very much for doing it.
So. Absolutely, my pleasure.
And lots of nice things there. So take care of yourself. And I hope to see you face to face sometime.
That will be nice. Absolutely. Cheers, Nigel. Thank you, and thank you, Molly, for organising things.
Yeah. Well, the students have been great. They did all the organisation. So.
Yeah, it's fantastic. Brilliant.
Thanks
All right,
ever
then.
so much, Jim.
Cheers. Bye-bye.
Okay, Molly. So, okay, all good.
Yeah.
Molly, you're muted.
Yeah. Sorry. If you could just pop into the breakout room that Anthony is assigning you to, Nigel, that would be great.